Hello, welcome back. So in the previous video, we saw how we can write kinetic energy in terms of our generalized coordinates and the speeds in those generalized coordinates. Now let's look at the concept of potential energy. Again, with the focus of writing these in configuration space and generalized coordinates. So again, the setting is similar. So consider the system of n particles and the how do I write it? And forces Fk and not a vector. So these forces Fk's being applied in any of these coordinates of n particles that we have. And these are applied forces, applied forces on particles. So that is our setup. Also, let's assume forces are all conservative. And if you recall, that means there is some potential function v, which is function of positions, or let's call it vx, but such that we can write this fk as gradient of that potential function along the direction of coordinate xk. So these are the conditions for a system to be conservative. Now going back to the idea of virtual work. So virtual work, if you remember, that is the work when we move our system in a way that is consistent with the constraint, and we assume no time has passed. So that's why it is called virtual. So virtual work is sum of, let's call it k equals 1 to 3n over all dimensions of fk virtual displacement xk. And I'm going to use this definition here. So it's going to be summation k equals 1 to 3n minus partial v partial xk delta xk. And this is actually the definition of full differential, but in this case, a virtual differential of potential function v, because if we had here, instead of delta k, we had dxk or delta xk, it would be potential, but now I have changed it to the virtual version. So in other words, very simply, virtual work is equals to minus virtual differential of potential function. So have that in mind. Now let's I don't write it down. Let's write all of these as a function of our generalized coordinates. So instead of v being a function of x. Now let's consider a v as a function of our generalized positions. So in this case, the differential of v is sum of j equals 1 to n. I have n generalized coordinates, partial v, partial q, this virtual displacement along q, j, j. And using this and that, we can see the virtual work is also, it takes a very similar form, j equals 1 to n, partial v, partial qj, this is q, and dqj. So we can still write the virtual work as a function of changing in the differential, but now the differential function, or sorry, as a function of differential of a potential function, but now the potential function is written in the generalized coordinates rather than our actual maybe Cartesian coordinates. And one other thing, recall from before, we defined generalized forces Qj. It was some kind of the effect of all applied forces along the direction of the generalized coordinate j. So it was so we had this. How do I write this? No, let me write it this way. That if we had that the virtual work, we could define it as summation over all these virtual forces, or I'm sorry, generalized forces, Qj delta Qj. And now let me do this too. This one and this one, compare these, we can see that our generalized forces are actually take the similar form of the partial derivative of v with respect to that coordinate qj. And notice similarity of this with that. So forces, either actual forces in our 3D space or the generalized forces in the configuration space, are always or are the partial derivative of a potential function with respect to whatever direction we are considering. But note here that this is valid, obviously, if all forces are conservative. And the last point here, also recall that what we call the principle of virtual work. System is in static equilibrium if delta W was 0. So that was the definition of this principle. If virtual work of all applied forces is 0, the system is in static equilibrium. And now, if all forces are also conservative, this means that if delta V is 0, system is in static equilibrium. So essentially, if you kind of draw the ball of potential function, if your system is at the bottom of that ball, or maybe it's a dome, if you change your system slightly and the potential of it doesn't change, that is what this statement means. Its gradient or its differential is zero in all directions, then your system is at static equilibrium. Is there anything else I want to add? No, I think that is all. So we saw potential energy and how it is related to potential function and generalized forces. We saw previously the concept of kinetic energy, how it's related to generalized coordinates. And the next one, we'll be looking at momentum in the generalized coordinates. So that's all I have for now. I'll see you soon.